Thanks, Yanai, and thanks you guys for inviting me. So I'm Omer from the Technion. This work is called Fiduciary Bandits, and this is a joint project with Gal Bahar, Kevin Layton Brown, and my advisor from the Technion, Moshe Tenenholz. This is us, people, society. Is it okay now? The other one? Yeah, it's kind of hard because I need to talk with my hands, so I'm not sure I'm capable of doing that. I'll try though. So this is us, people, society, and this is an AI system, okay? Now we are using such system extensively to make our lives better, to make decision-making better, facilitate decision-making, make smarter decisions, and even make decision-making completely automated. And sometimes we have a set of alternatives that we should pick from. This is just a spoiler. Later on, I'm going to adopt a multi-arm bandit model. So we should pick the best or the most rewarding alternative, but we don't know what that alternative is. So we use an AI system to make the decision for us. And in the process of picking the best decision or the best alternative, such an AI system must, by definition, explore all options. And if it's going to explore all of the options, it also means that it's going to select or to pick with some probability, very high probability, some set of the users and make them and sacrifice them for the sake of society. Make them pick an a priori suboptimal alternatives. So sacrificing an individual for the sake of society seems a bit wrong. It might be unethical or illegal even in some situations, such as banking or healthcare. And so we wanted to tackle this problem and maybe come up with more attractive AI systems. So we introduced this stylized model and we ask 3 questions. First, what are some meaningful individual guarantees in this space to make the system more attractive, not only in the eyes of its users, us, people, but also in the eyes of the regulator, okay? Given that we have some strong individual guarantees that the system can provide independently for each one of the users, we still want to maximize the social welfare. So we still want to have optimal algorithms and hopefully efficient ones. Third, we're going to ask, okay, so you are going to impose some constraints, some guarantees. You want to have these guarantees. So the welfare is going to decrease. By how much? This is the formal model that we adopt. We have a set of K arms. The reward of each arm, I'm going to denote it by the random variable xi with an expected value of mu I. Assuming that these are mutually independent. Without loss of generality, I'm also going to assume that those rewards are sorted according to decreasing expected values. For the sake of this presentation, I will assuming that every such xi takes values in the set of integers between 0 to h, but in general, we can solve the problem for any finite set. And just notice that these are static. Namely, if I tell you what's the value that xi takes, then it's going to be the same for the rest of the execution of the algorithm. So if I know that, just a reference to Ishai's work, if I know that a road takes 20 minutes to drive, it's going to remain still throughout the entire day. It's going to be static. We have n agents where I'll simply refer to agent I as the agent arriving at round I. And I'm also going to assume for most of this talk that agents follow the mechanism. So once the mechanism pick an arm, an alternative for an agent, the agent will adopt it. Okay? Later on we can relax it and still some of the results will carry on. What's a mechanism in this context? It is a mapping from histories to actions, possibly randomized actions. So a history is a tuple of pairs, action, reward, action, reward, action, reward. Given that, the mechanism should decide for the next agent what alternative to pick, what arm to pick. Okay? And as I told you, that action could also be a randomized action, namely picking arm 1 with probability half and the other arm with probability whatever that is. Some mixture over the arms. We still want to maximize the social welfare, which is basically the average reward. Okay? Now, it's really obvious that if you want to maximize the social welfare, here is the easiest way to do it. Just explore each one of the arms, right, sequentially. After K agents, you know the rewards of all the arms, and then just exploit the best one. Okay, this is a full exploration policy. What's the problem with this policy with respect to what I've told you earlier? You're going to sacrifice some of the agents. The mechanism is going to pick consciously and deliberately arms which are a priori suboptimal for some of the agents. My wife works at Waze and they claim that they don't, but I don't believe them, so I guess you're right. I do believe my wife though. Yeah. So here are the two axes we care about. First, we have the welfare. We want high welfare, definitely. But we also want to have individual guarantees, guarantees that the system can provide to each one of its agents independently of the other. So I'm going to refer to it as something that is qualitative, but you can think about it as the expected value, the minimum expected value over all possible agents. So we have the policy that I've told you earlier about, full exploration. And we want to have high welfare, but we also want to have individual guarantees, so we have this curve. And I'm going to show you today three definitions of individual guarantees. Some of them are strong, some of them are weak. And as you can imagine, as you impose stricter guarantees, the social welfare, the highest possible social welfare under that guarantee is going to decrease. So I'll start with the fiduciary. If you're a non-native English speaker, then you might not know what a fiduciary is. And as it turns out, even if you are a native English speaker, you might not know what a fiduciary is. So here is a definition from Wikipedia. Sorry. I'll just read it. A fiduciary is a person who holds a legal or ethical relationship of trust with one or more other parties. So all of you know fiduciaries. These are your financial advisors or financial planners. These carry by law a fiduciary duty and must intuitively operate in your best interest. So when you hand over your money to the bank must handle your money as if it was as its own. Okay? And intuitively, in the terminology that I have showed you earlier, we say that a mechanism M is a fiduciary if for every agent L and every history that precedes agent L's arrival, and any other mechanism M prime, this inequality should hold. Let me break it down for you. On the right-hand side, you get, you have the expected value of that arm selected by the mechanism M prime when it sees the history H, given the history H. Now on the left-hand side, we have the same for the mechanism M. So you can see that basically being a fiduciary guarantees every agent that the mechanism maximizes its expected utility. And from an algorithmic point of view, this is kind of trivial because it characterizes the greedy algorithm, right? I guess you can see that. Great, so I'll skip the middle definition for now and just move to individual rationality. I should probably say a thing or two about what agents know. Okay, so in our model, so far agents cannot do anything other than adopt the mechanism's, I won't call it device, the mechanism selection. But we should say a thing or two about what agents could have done before the age of AI. Okay, so when I drive, for instance, from Haifa to Tel Aviv, there are several roads, and there is my default road, the road that in general, on average, is the fastest one. Okay? So I'll refer to this concept as the default arm, the arm that the agent would have adopted hadn't she used the mechanism. And without loss of generality, this is the hardest case to analyze. I'm going to assume that the default arm of all agents is the first arm. Recall that the first arm, A1, has the highest expected reward. Okay? You can probably see why this is the hardest case to analyze. Otherwise, I can just send or pick alternatives for each agent such that all the default arms are explored, and then we can just move on after exploring all possible arms. Great. I'll say that a mechanism is individually rational if every agent is in expectation weakly better off using the mechanism, okay? Weakly better off using the mechanism. And this should hold according to the mechanism's knowledge, not the agent's knowledge. So we kind of abuse the information asymmetry here. Formally, it goes as follows. A mechanism M is individually rational if this inequality holds, and this is a bit more harder to digest. On the right-hand side, what you have is the expected value of the reward of arm number 1 given the history. Arm number 1 is the default arm. So what you have on the right-hand side is what the agent would have gotten had she used her default arm and not the system. And this is computed according to the mechanism's knowledge. Okay? On the left-hand side, we have what the agent would get if she uses the mechanism. Okay? This is the expected value of the agent given what the mechanism knows. Let me exemplify, because I know it's kind of hard to digest. We have on top the IR constraint, and let's say that there are 4 arms, and they are sorted according to decreasing expected utility. Now, for the first agent, the mechanism knows nothing, okay? Only the prior over the alternatives, the arms. So on the right-hand side, E of x1 given h, this is basically 20. This is what the mechanism believes that the expected value of the default arm is. So the mechanism is free to pick any distribution over the arms such that the expected value over the randomness of those rewards and the lottery is greater or equal to 20. Obviously, the only way to do so is to pick arm number 1 with probability 1. So this is what the mechanism would do for the first agent, and let's say that the realized value is 17. Okay? Now, the right-hand side is now different because the mechanism knows that the expected value of the default arm, given what it knows, it knows the realized value, so this is 17 now. So the mechanism is free to pick any distribution over the arms with an expected value greater or equal to 17. Again, the only way to do so is to pick arm number 1 with probability 1. Yeah? No, they are mutually independent. I'm assuming a bit more than, yeah, they're mutually independent. I'm assuming independence, yeah. Great, so in this case, there's nothing the mechanism can do, and it would end up.
So this, like the right-hand side here is either the realization if you already realized it, or just the expectation?
Exactly, exactly. It has two possible, two options. So in this case, we would have no exploration whatsoever. However, let's say that the realized value of arm number 1 is 12. In this case, the right-hand side is 12, and now the mechanism can do a bunch of things. For instance, it could pick arm number 2 with probability 1. But it can also do a much more complex selections. For instance, it could pick some mixture over the arms. Yeah, sorry.
On the right side, you have expectation over x1 given x. So shouldn't that be 20? I mean, maybe I'm
So now the history is picking arm number 1 and seeing a value of 12. So the history specifies what's the value of x1.
I see. So that should not be expectation. Then you're actually looking at.
You look at the expectation of a constant value. This is the thing, right? You already know what's the value of x1. So I was about to say that it could also pick a mixture over the arms. And one such mixture is picking arm number 2 with probability half and arm number 3 with probability half. And why this is valid, you can go through the simple computation. You would get an expected value of 12.5. So you can probably see that satisfying this IR constraint is not really hard. For instance, if you just go greedily, being a fiduciary, then you would satisfy this constraint. Remember that the challenge is not just to satisfy the IR constraint, but to maximize the social welfare. So we want high social welfare subject to satisfying the IR constraint, and it's quite obvious from this example that if you pick the wrong exploration policy, then you would end up with suboptimal welfare. If you just try to explore arm number 2 with probability 1, you might end up stuck. not exploring arm number 3 or arm number 4, whereas if you pick another mixture, such as the one given here, probability half arm number 2, probability half arm number 3, you can potentially explore also arm number 3. So I would argue that given infinitely many agents, or if the number of agents is large enough, any mechanism that seeks to explore as much as it can will eventually end up in one of these two states. Either it observed an arm with a reward which is greater than R1, provably greater than R1, the realization. And in this case, I'll just refer to it as a jackpot. On the other state, the other case is when it cannot explore anymore because all the observed arms have realized values which are less or equal to R1, and all the unobserved arms have an expected value which is less than R1. This is a failure. Now, if we get into one of these two states, continuing in an optimal manner is really easy. If we hit jackpot, then we can use that arm in order to explore all the other arms. And if we are on failure, then the only thing we can do is to pick arm number 1, the default arm. So you can see that everything boils down to how you explore the arms. How do you explore the arms using the first k or less agents? So this could be modeled using a Markov decision process, or more precisely, a goal Markov decision process, where rewards are only obtained at the absorbing states. But it has some complexities. For instance, you have a continuum of actions. So there is a continuous set of actions that you can pick from in each one of these states. So this is kind of delicate, and it's non-trivial to get the optimal policy of that MDP. Okay, I'll just keep the example, and now I'll.
So what is the state of the MDP? Those are these states?
Yeah, it's a mapping from. Okay, so you don't need. It is finite. It is 2 to the power of k states. I'll talk about it, and I will mention it. So let's say that we've been able to find that optimal policy. Let's call it pi star. Now, an asymptotically optimal IR algorithm goes as follows. Offline, we compute it, pi star. Then we continue as follows. As long as we didn't hit one of these two terminal states, jackpot or failure, we simply we tell pi star, this is the state. We get an action from pi star. This is a randomized action. We flip coins according to it. And then we tell the corresponding agent, this is what you should do. We do that until we hit one of the terminal states. If this is the jackpot, then, as I said, we can mix the provably better arm with every other arm. And so after a reasonable amount of time, we will, with probability 1, explore all the arms. And then we can exploit. If we hit failure, then we're doomed. We cannot explore anymore, R1 to every subsequent agent. A thing or two about that optimal policy. So we have we have characterized some properties of that optimal policy of the MDP in general. We show that there exists an optimal policy that picks 2 arms at a time. So we don't need to consider mixture over all arms. And even more than that, we can tell what those probabilities are. So eventually, we take a continuous set of actions and we reduce it to something which is roughly k squared.
I'm slightly confused, Ben, to my thought, because it's thinking of a different model. What do the agents see the history?
Okay, the agents are not strategic in this model.
It's an IR model.
Right.
So IR with respect to what?
IR with respect to the definition I gave earlier.
Only X1.
Only? X1.
So
Yeah.
Okay.
Right. X1 versus what the mechanism gives. This is another way of looking at it.
Would have been sort of with respect to the history the best thing that you could do.
Right.
Then this would have.
It shouldn't surprise you because solving optimally for k arms, even in your model, is still an open problem. Yeah. We didn't. I have that in mind. Yeah. Great. On the downside, solving for that pi star takes a runtime of 2 to the power of k times the minimum between k and h. K being the number of arms, h is the size of the support. So this might look kind of discouraging, and it is. But on the other hand, two things. First of all, you don't see the number of agents here. And this is the parameter that scales. This is what we care about in the problem. And second, everything here could be, computing this policy can be done offline. So we don't need to wait between the interaction of two agents. We just run everything at night, assuming that we can, and then everything follows smoothly. The theory that accompanies this algorithm is that its social welfare is greater or equal to the optimal, the highest possible social welfare of any IR mechanism times some factor that goes to 1 as n increases. So I have 3 more minutes, right? Yeah, cool.
2.5.
2.5. Great. So I'll skip this one. This is just relaxing relaxing the individual rationality constraint and saying that the mechanism cannot perform lotteries over arms. I'll skip this one. And finally, the last thing that we think that is interesting in this case, I've just figured this curve and put the dots on it. So you might ask, okay, I'm not doing full exploration because you have convinced me that individual guarantees are important. Now what? How much should the welfare deteriorate if I implement each one of those guarantees? So I don't have a definitive answer. I do have some examples. There are 3 quantities we care about. Opt is the optimal social welfare, the highest possible, obtained by full exploration. Opt-IR is the highest possible social welfare of any IR algorithm, and Opt-EPIR is the optimal social welfare of that ex-post individually rational mechanism that I didn't talk about. So here we have an example, and we have an instance such that the ratio between the optimal social welfare and the Opt-IR is greater or equal to, think about the regime where K is roughly H. So this is a constant times H. And again, this is discouraging. It means that you're going to implement strong individual guarantees, then you're going to give welfare away. But this is some sort of a worst case. We also have examples where this ratio is less or equal to a small constant, a constant that is close to 1. We also show that the algorithm that I've talked about is essential if you will have lotteries over the arms, you could improve the welfare a lot with respect to, or with comparison to the case where you don't perform lotteries. So I have a slide on incentive compatibility, but I won't go through it in the interest of time. And let me just conclude. We've talked about explore and exploit scenarios, and I'm advocating for individual guarantees for this system, such that the system won't sacrifice individuals, or maybe if it is, it could still satisfy some strong guarantees that would make it more attractive. I've showed you optimal or asymptotically optimal algorithms. We also have IC under some constraints. There are plenty of technical open problems and also conceptual open problems. And I'll finish with that. Thanks.
So when you gave the plot, it looked very much like a concave function.
Right.
And it made sense, but can you show that it's indeed concave?
I cannot show
like
it.
at the 4 points only.
I cannot show it. I think that...
So a linear interpolation, like you can have a point which is below linear interpolation of 2.
I think you can. So we have these examples showing that things can go off, could go sideways, and there are cases where it could be just the same as exploring all arms. So I'm not sure what is the right curve to draw here, but this is my drawing capabilities. So.
Drawing was great.
I have time for one more question.
Yeah.
What is the uniform arrival?
Yeah, so in the work of Ilan Kremer, Ishai Mansour, and Moti Perry, they assume that each and every agent knows its place in line. you can think of alternative model where there is some stochasticity on the agent arrival. So if the agents arrive uniformly, so think about all permutations, you just draw one, then everything, all the algorithms that we have are IC as is. If this is not the distribution, but there are some conditions that hold, we can still have IC. So
Okay, thank you very much.
thanks.